The title of my presentation is Deep Learning for Manufacturing Inspection Case Studies. My name is Stephen C. and I'm with FLIR Systems. Here is the outline of my presentation. I'll start with an overview of manufacturing inspection applications and how deep learning can be used for such applications. I'll then talk about the deep learning workflow and present a few case studies of manufacturing inspection applications. At the end, I'll share some best practices that we have learned. Let's start with a brief overview of manufacturing inspection. Deep learning is now revolutionizing the machine vision industry. Machine vision industry is shifting from traditional rule-based approach to deep learning. Traditional methods require handcraft algorithms by skilled engineers with programming and vision expertise. Deep learning can adapt to new examples without reprogramming. Therefore, tedious programming for identifying different defects is no longer necessary. For instance, instead of programming code like this, isn't it great that we can just show a bunch of good and bad examples? Deep learning is very well suited to many machine vision applications, such as manufacturing inspection, defect detection, classification, segmentation, etc. Textile inspection is a good example where traditional methods do not perform well after years of development, while deep learning can outperform them after a few minutes of training, provided that you have the training data, a suitable model, and training parameters. In this example, the defect is detected, and the zoom-in view is circled in blue here. Here are some other examples, such as machine part inspection and solar panel inspection, where deep learning works well. The zoom-in view of the defects detected are circled in blue here. It is very difficult to model a defect mathematically and hard to come up with an algorithm to detect any type of defects. Deep learning is highly suitable for manufacturing inspection applications where the setup and lighting are well controlled and do not change much over time. Some setups are shown here where the object is in a predictable location and is not affected by ambient lighting. As a result, relatively few training examples are needed, such as tens or hundreds of images. And the training can be done on standard laptop or desktop within minutes or hours. So if you are interested, how do you go about applying deep learning to such applications? One approach is to make use of commercial software packages tailored to manufacturing inspection applications. They provide end-to-end solution from image annotation GUI to training and inference tools. Examples of such software include Cognex VD, MV Tech Halcon, Adaptive Vision Studio, etc. The other approach is to make use of open source frameworks and tools such as TensorFlow and Caffe. This is the approach we'll be using for our case studies, and I'll explain in more detail shortly. While deep learning is great for many applications, it shouldn't be regarded as a panacea that solves all our problems. The traditional rule-based methods are still more suitable for certain applications such as dimensional measurement, code reading, robot guidance, precision alignment, etc. Some of these examples are shown here. Deep learning is more suitable for applications with deformable objects, variable orientation, weight specification, where traditional methods are more suitable for applications with rigid objects, fixed orientation, formal specification. For some applications, hybrid approach could be used where traditional methods can complement deep learning. For example, you may use deep learning to detect where a barcode is and use traditional methods to read the code. Let's talk about the deep learning workflow. Here is the workflow from training to deployment. You start with data collection and annotation. Optionally, you can augment your training data with more variation, and then run the training, which can be done locally or in the cloud. You would then evaluate the model performance and may need to iterate the process repeatedly until you are happy with the performance. More training data may be needed, or some training parameters may need to be adjusted, and so on. In terms of tools, you can use open source frameworks such as TensorFlow and Caffe for the training. For deployment, you will use the trained model to run inference, and the output results could be labels for classification or bounding boxes for detection applications. For deployment platform, you can use a single board computer with an Intel Movidius neural compute stick, which can run inference efficiently using the Intel Movidius VPU. In order to use the neural compute stick, you need an extra step to convert the TensorFlow or Caffe model into Movidius format using NC SDK or OpenVINO from Intel. As shown in the workflow, we need to collect data and label them before we can train the model. Assuming you cannot download images for your application from the internet, you will capture actual images or generate synthetic data or do both. If you are capturing images, it's important to ensure the setup is similar to deployment, such as lighting, camera, optics, etc. If you are to generate synthetic data, one key benefit is that labeling is not needed. It is important to have accurate data labeling, as even a few incorrect labels could adversely affect the resulting model. For classification applications, you will simply divide the images into folders corresponding to the different classes. For detection applications, you also need to provide bounding boxes of the objects of interest as well. There are open source tools available to help with annotations, such as the one shown here. As you can imagine, data collection and labeling are tedious and time-consuming. Fortunately, we can expand and diversify the training data using a technique called data augmentation. The idea is to perform image processing on the collected images, such as rotation, scaling, changing brightness, etc. Then you don't need to capture actual images by rotating the camera, moving the camera closer, and so on. Some examples are shown here. This could improve deep learning inference accuracy without collecting more training data. This can be done before training by saving the augmented images to files or on the fly during training. To learn more about this, please check out Evan Jura's talk on data augmentation. Typical deep learning models have millions of parameters and takes weeks to train. For example, models for the ImageNet Visual Recognition Challenge were trained on multiple powerful GPUs over a few weeks using over 1.2 million training images. What if you don't have a million training images for your application or don't want to wait for weeks of training? Fortunately, we have a technique called transfer learning, which can shortcut a lot of this work. It can take a fully trained model and retrain it for new tasks. For example, here is a network trained for task 1. We can use these layers as a feature extractor by keeping the weight fixed. Since the last layer is task specific, we just retrain the last layer for a new task. As there are much fewer parameters to train, it requires much less training data and it is much faster to train. One of the recent trends is towards smaller convolutional neural network models. They are more practical for mobile and embedded vision applications. They have less parameters and therefore can be trained with less training data. And you require less bandwidth to send a new model from the cloud to the edge. Many such models have been developed recently, such as SqueezeNet, MobileNet, etc. This table compares the various models in terms of computation, size, and ImageNet accuracy. The ones highlighted in green are much smaller and require fewer operations, but still achieve similar accuracy as the larger models. I'll now talk about a few case studies on manufacturing inspection applications. In this case study, we would like to classify between good and bad pills, which could have scratch, dirt, chip, or any visible contamination as circled in red here. We collected our data in a well-controlled environment using a black background to increase the visibility of the white pills. We selected a suitable lens and a camera height to capture fine details on the pills, and we labeled the images by putting the good and bad images into separate folders. We used an open source augmentation library to generate more training images from the collected data. The augmentation includes rotation, shearing, distortion, perspective transform, as well as chaining several of those operations as well. Some of the augmented images for this sample image are shown here. We collected relatively few training data, 37 good examples and 54 bad examples, and we used data augmentation to expand them into around 10,000 training images for each class. We used MobileNet V1 for transfer learning and changed the last classification layer from 1,000 classes to 2 classes, and we trained that layer. Our proof of concept achieved 94% accuracy. We noticed that there is a large difference in confidence for the same pill at different locations, which means it could benefit from more training data or better augmentation. In the next case study, we would like to develop a deep learning solution to inspect our own camera cases, as some camera cases from our supplier could have defects, and we don't want to use defective cases in our cameras. We collected training data for 3 classes, good, bad, and not ready. Bad examples may include scratches, dent, logo scratches, and any other imperfections as circled in red here. Not ready means it cannot see the complete camera case or the camera case is not placed properly. When we were collecting the training data, we realized that there are various imaging challenges. For example, some defects may be more visible depending on the camera exposure setting. At this exposure setting, we can see some defects better than the other exposure settings and vice versa. Moreover, whether the light is diffuse or directional could also affect certain defects can be observed. For example, this scratch can be seen under directional light, but not as clear under diffuse light. We built a prototype system that consists of a camera, a single board computer, and a neural compute stick as shown in this photo. Under well-controlled setup and lighting, we use MobileNet for transfer learning using relatively few training images. To speed up performance, we pruned the MobileNet V1 network by keeping just the first 7 layers to retain and their weight to retain the low-level image features. We changed the last classification layer from 1,000 classes to 3 classes, and we trained that layer. This proof of concept produced 97.3% accuracy, and it runs at 24 frames per second with the neural compute stick. This video shows the classification results as the camera cases move through the camera view on the turntable, whether the image is good, bad, or not ready. It will say not ready when it cannot see the complete camera case. In the final case study, we would like to develop a deep learning solution for PCB hand soldering inspection. Here are the 2 sides of the PCB board for our camera. There are 3 locations that require hand soldering where operator errors can occur: the LED light, the GPIO connector, and the RJ45 connector. We want to classify good solder versus missing or bad solder, and we need to inspect multiple regions of interest. Such inspection would be useful for quality control. For those who may not be familiar with soldering, here are some common soldering problems. Solder bridge may connect 2 pins unintentionally. stray solder spatter may also connect two pins unintentionally. Other problems include lifted pad, untrimmed leads, etc. And all of the above problems can happen on a single PCB too. As you can see here, there are many variations of a good solder and a bad solder, and it is quite subjective, which is a difficult problem for traditional methods and can be better handled by deep learning. For each region of interest, we collected 80 images in total, some good and some bad examples, which could be missing solder or other defects. For the LED region, here is a good example, and here is a bad example where the solder is missing for all the pins. For the GPIO region, here is a good example, and here is a bad example where the solder is incomplete for one of the pins. For the RJ45 connector region, here is a good example, and here is a bad example where there's a solder bridge. Here is our PCB hand soldering inspection setup. Since the region of interest are on both sides of the board, we 3D printed a carrier like this with LED ring light both above and below, so that we can put a camera above and another camera beneath the carrier to perform inspection simultaneously. For each region of interest, we use MobileNet for transfer learning, where we keep all the layers and their weight, and just modify the last classification layer from 1,000 classes to 2 classes, and retrain that layer. This proof of concept achieved over 95% accuracy. This video shows our prototype system. After a PCB on the carrier has been inserted, it will indicate the inspection result using a green or red LED light for pass or fail, as circled in yellow here. We have plans to improve this further and deploy it for production use at FLIR. In all 3 case studies, we use a supervised classification approach, which requires considerable training data for the good and bad classes. However, in many manufacturing inspection applications, there are typically many good examples, but very few bad examples. Therefore, there is a large class imbalance even after augmentation, which is not desirable for deep learning training. Another approach for this type of application is unsupervised anomaly detection, where only good examples are needed to train the model. Here is an example of anomaly detection where it will segment the pixels or regions that differ from the model to detect the anomalies. For the case studies, we collect more bad examples in order to apply the classification approach, which can be handled by a smaller network and deployed on the edge more easily. We are currently looking into using anomaly detection in these applications. We would like to share some best practices that we have learned from the case studies. Training images must resemble inference images at deployment. For example, object position should be consistent, lighting, camera, and lens should be similar. As data collection is typically very tedious and time-consuming, it is better to optimize the physical setup to simplify the problem, rather than trying to handle diverse conditions. For example, color-related problem could be solved by using monochrome camera. We can select cameras with sufficient resolution and dynamic range to capture the fine details. As shown earlier, lighting could help highlight differences between classes. The reduction of complexity allows the use of smaller network, requires less training data, and can train faster. It is crucial to apply the same image processing for training and deployment. For example, if you resize your images used with anti-aliasing during training, but resize without anti-aliasing during inference, these jagged edges, as shown here, would adversely affect the accuracy. Let's summarize the lessons learned. Deep learning is revolutionizing the machine vision industry, where deep learning excels in many classification and inspection tasks compared to traditional rule-based methods. I presented a few case studies on manufacturing inspection, showing that deep learning is highly suitable for such applications, thanks to the well-controlled setup and lighting. Unlike many other applications where tens of thousands of training images are needed, relatively few training images are sufficient. Rather than training from scratch, transfer learning works well, which makes short training time feasible. Deep learning inference on the edge is feasible, as there are smaller networks available, which are practical for embedded vision applications. Here are some resources for those of you who would like to learn more about deep learning for manufacturing inspection applications. These are some commercial deep learning software packages I mentioned earlier, which are tailored to manufacturing inspection applications, and they provide a number of use cases so that you can see whether and what types of applications have worked well. Here is a tutorial on using TensorFlow open source framework to build an inexpensive deep learning classification system based on the workflow I presented earlier. And here is another tutorial on some tips for creating training data for deep learning models. Finally, I'm proud to introduce our Firefly Deep Learning Inference Camera, which combines essential machine vision features with the power of deep learning. It can perform inference on the edge efficiently with the integrated Intel Movidius VPU. Instead of using a single board computer with a camera and a neural compute stick, we can now do the manufacturing inspection just using a Firefly camera. Being industry's first deep learning-enabled camera with best-in-class imaging performance, small size, and low price, we are pleased that Firefly received a Gold Innovators Award from Vision System Design last year. Thank you for your attention.